Okay, so this is the second to last unit of the class. So you guys are doing great getting to the finish line. So what we're going to do to start out is we are going to revisit a definition that we saw as part of the first unit. And that is the definition of what a function is. So this is just at the top of our page. Function is a relation. So again, just refreshing your memory because it's been a long time since we talked about it. A relation is just a set of ordered pairs. Okay, so a function is a set of ordered pairs in which each element in the domain corresponds to exactly one element of the range. And we've been doing stuff with functions the whole time. We had our 6 basic functions, then we added in a couple rational functions, and we have the vertical line test to determine if something is a function, and that gives us the picture. So each x corresponds to exactly one element of the range. So now what we're going to do, and we're going to spend our section 6.1 talking about, or this whole unit, is a specific type of function, and that is what's called a one-to-one function. And in fact, in this definition, we are going to just change one word. So a one-to-one function is a function in which each element in the domain corresponds to a unique, okay, so I've bolded it and italicized it, I'll even underline it, a unique element of the range. So no longer will we have repeating y values, okay, so it's still a function. So meaning when we look at our sets of ordered pairs, each x is listed once. And now, since each element of the range is unique, each y will also be listed once. There's no repeating anything. That's what it means to be one-to-one. So my first example, I've already telling you that this is a function. And I want to know, is this function a one-to-one function? So do I have any repeating y values? So 1, 5, 9, -6. So is this a one-to-one function, yes or no? Yes, no y values repeat. So yes, this is 1-to-1. Fantastic. So if you would do me the favor of exercise 1 and exercise 2 that are over on the right, go ahead and determine, are each of those 1-to-1? Yes or no? Okay, so exercise 1, what did you say for that one? Is this 1-to-1, yes or no? No, it's not. Why not? Perfect, the 3. I have a y value that is no longer unique, so this one is not 1-to-1. All right, exercise 2. How about exercise 2? Is that function 1-to-1? Yes, it is. None of the y values repeat. I've got a 2, a 4, 6, 8, a 10. So this one is 1-to-1. 1-to-1 means for every x value, you have your own individual unique y value. There is a 1-to-1 correspondence between that. So here's what I would like you to do in example 2. Example 2 starts off just as a review of something we've been doing a bunch of this whole semester. So just graph x cubed plus 2. X cubed plus 2. It's one of your basic functions, and then we've added 2, so hopefully you remember what that means. Then we're going to determine, is that a 1-to-1 function? So this is, if you remember, we're going to take the x cubed graph, we're adding 2, so that's going to shift the whole thing up 2 units. Okay, so I'm going to just start over here. When I take 2 and cube it, I get 8, and then I add 2 and it becomes 10. When I take 1 and cube it, 1 cubed is 1, and when I add 2, it becomes 3. 0 cubed is 0, and then I add 2, it becomes 2. Negative 1 cubed is negative 1, and then when I add 2, it becomes positive 1. And then finally, negative 2 cubed is negative 8, and when I add 2 to it, it becomes negative 6. So this hopefully is the graph that you're looking at. It's your x cubed function that's been shifted up 2 units. So that right there, that part of it is review. Here is the new part. The new part is that a one-to-one function? Do I have any y values that are repeated on more than one point? No. So let me just draw some lines here. So here's the y value. Here's the y value 8, and I only hit the graph one time. There's only one y value. Here's the y value 5. I only hit the graph one time. There's only one y value. Here's the y value. Let's go negative 6. It hits the graph one time. So because of that, because every horizontal line I draw only hits the graph at one point, that means each of those y values occurs once. And so this is indeed a one-to-one function. So again, if you remember way back when we first started chapter 2, we reviewed, because this was part of intermediate algebra, that the test to see if something was a function was the vertical line test. Does each x value happen once? That was the big deal. And so now, to supplement that, you could see the test to see if something is one-to-one is the horizontal line test. If a horizontal line hits the graph one place everywhere, you have a one-to-one function. Okay, so the horizontal line test, which you can't see me writing because it's off the screen, so let me slide this up here. The horizontal line test simply says if a horizontal line intersects a function always at a single point, the function is one-to-one. Horizontal line test says if I draw a horizontal line and it hits my function, okay, because we're talking about functions, if it hits my function everywhere at a single point, that function is a specific type of function called one-to-one. Every x value corresponds to a unique y value. So what I would like you to do once you're done, if you have any questions, ask it. We're pretty casual. There are just a handful of you here, so I can answer every single question you could possibly want to ask, and we'll have time left over. So I would like you in exercise 3 to graph x squared minus 4. And then I would like you to use the horizontal line test to determine, is that a one-to-one function? Does each x get a unique y value? Okay, so again, if you remember our transformations, this is my x squared graph. It's just been dropped down 4 units. So again, when I square something, when I square 3, it becomes 9. When I drop it down 4, it becomes 5. When I square 2, it's 4. When I drop it down 4, it's 0. Squaring 1 is 1. Drop it down 4, it's -3. Square 0, it's 0. Drop it down 4. -1 squared is 1. Drop it down 4 to -3. -2 squared is 4. When I drop it down 4, it becomes 0. And finally, -3 squared is 9. Drop it down 4, it's 5. So here is my graph. Beautiful parabola. And then the big question. So that should be review. Hopefully that seems like settled business to you. So now, is that a one-to-one function? No. We can see, I'm just going to draw one horizontal line. We see that y values are repeated. This y value occurs twice. So even though that parabola, that pink parabola is a function, it is not a one-to-one function. Okay, so there we would have to do something to that if we want to use the applications of one-to-one functions. We good? We're starting to see, I know this is a difficult concept, it's new and different. So if you have any questions about one-to-one and what makes something one-to-one, that I would love for you to ask it and make me feel like I'm earning my money today. All right, so let's do one more. Exercise 4. Again, part of the purpose of these problems is we're reviewing our transformations, bless you, and then we're reviewing our transformations and then determining if something's one-to-one. So there's my square root graph. So go ahead, please, and draw that, and then determine if it's one-to-one. Okay, so for this square root graph, there's a +3 underneath the radical. What does that tell me to do with my graph? Goes left 3, great. So I moved my whole square root graph left 3. So I've got this, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So here's my graph that's been shifted to the left 3 units. Beautiful. Okay, now when I perform the horizontal line test, is this a one-to-one function? Yes, a horizontal line is always going to hit this graph at one point. And so, yes, this is a one-to-one function. All right, well, that's great when we're given a graph or we're given a set of ordered pairs. But what happens if I'm just given an equation? So for instance, like example 3 that I'm going to do with you. Okay, so we're going to determine analytically if f of x is equal to x cubed plus 2, if that is a one-to-one function. Okay, so here's how you do this. Again, I know this is new and different, so if you have any questions, the key concept of one-to-one is that y values don't get repeated. Okay, so the way that we start off this test is this. We say, okay, we're going to pretend that I have y values that are repeated. We're going to say that the function value that's associated with the x value a is equal to the y value associated with the x value b. So we're going to say, what happens if y values are equal on this function? And I want to know, does that mean they come from the same x value, or does it mean they come from different or can they come from different x values? So notice we already showed by the graph that x cubed plus 2 is 1 to 1. Okay, we know that that's the result we're anticipating. So let's do this analytically. So what I'm going to do is I'm going to take a and I'm going to plug it into the function. So when I plug a into this function, what do I get on the left side here? Perfect. A cubed plus 2. All right, what do I get when I put b into this function right here? Okay, b cubed plus 2. And then what we're going to do at this point is we're just going to go ahead and solve for, it doesn't matter which one, I'm going to solve for a. I could solve for b, it really doesn't matter. And we're going to see what happens. Okay, we're going to solve for a. So first thing I'm going to do is I'm going to subtract 2 from both sides. I'm going to write out all the work just so that there's no confusion when you're leaving here. So we have a cubed left on the left side. We have b cubed left on the right side. And then if I'm solving for a, I'm just going to go ahead and do the cube root of both sides. So here we go. We'll cube root of both sides. So cube root of the left, the cube root of the right. And what I end up with is that a equals b. Okay, there's no plus or minuses. We only do that when we're doing square roots, things of that nature. So what this is telling me, here's how this becomes the test. This tells me that if I start off with equal y values, they had to come from the same x value. And that's the definition of 1 to 1. 1 to 1 means each x value gets a unique y value. Okay, so this y value here could not have come from different x values. And so for that reason, this is a 1 to 1 function. All right, so what I would like you to do, please, is take your hand first at trying exercise 5. Exercise 5 is just a line. You can probably visualize it and see that it's probably going to be 1 to 1, but I want you to show analytically that that has to be true. All right, so I'm going to ask you to do this on the test. I'm going to ask you to do this twice, I promise. So next test, you can put an asterisk. In fact, I'm going to ask you to do all these things on the test. So all this is the test that we're going through right now. So what you're going to do always when you're doing this analytically is you're going to start off with this statement. Function at the x value a is equal to the function at the x value b. We're going to say, okay, we're going to assume this and we're going to see what is the consequence. So when I put a into this, hopefully on the left, you have a 5a minus 2. And on the right, you have a 5b minus 2. I'm now going to solve for a or solve for b. It does not matter at all which one. So I'll add 2. I'm going to write all the steps so that there's no confusion or consternation here. Then I'm going to divide both sides by 5. And once again, we end up with this statement that a has to be equal to b, meaning they have to be the same x value. If this y value is going to be repeated, it has to have come from the same x value. So what that means is this is 1 to 1. Each x value gets a unique y value. Try the same thing for exercise 6. If you have a question, be sure to ask it All right, so again, start off with this statement. This one's a little bit harder. There's a few extra steps. So if you missed something, let me know. So we start off with the statement f of a equals f of b. What happens if those y values are the same? Okay, so I'm going to plug a and b into this function. So I get the square root of 25 minus a squared is equal to the square root of 25 minus b squared. And now I've got to just gradually unpeel the layers here until I solve this for a. So what would you suggest my first step is solving for a? Yeah, let's square both sides. Perfect. We've got to get rid of those square roots. So we'll square both sides of this. That sounds like a fantastic idea. And when I do that, I have 25 minus a squared is equal to 25 minus b squared. So far, so good. The next part I'll do, I'm just going to get rid of those 25s now. So I'm going to subtract that from both sides. Okay, so far everything's looking great. If you don't know why I'm doing something, let me know. I have negative a squared is equal to negative b squared. So again, I'll give you this next one. This is just introductory algebra stuff right here. I'll divide by -1. And now I have the statement a squared equals b squared. What am I going to do to solve this for a? One more step. Perfect. Square root both sides. And then here's the thing to remember. I've mentioned this before in this class. I'll repeat it all again. When you impose the square root on a problem, there becomes two answers. Okay, you can get a plus or a minus b. Talked about this when we talked about solving quadratic equations. I'll put this back on the screen in a minute, but the question might be, you might have forgotten because it's been a while, why? And that's a great question. So for instance, with some numbers, if I have x squared is 16, if that's an equation I'm solving, and I say, okay, to solve that, I got to take the square root of both sides. I do that. Square root of x squared is x. Square root of 16 is 4. But remember, when we solve something, our check is to just go back up the ladder. So what numbers can I square to get 16? Well, certainly 4, but also if I square -4, -4 times -4 would give me 16. So both of those become legitimate answers. So that's why we have to have a positive and a negative. So here's the thing. If I have equal y values, that means they came from different x values. Okay, there's more than one. There's a positive and a negative. So now the y values are no longer unique. So because there's more than one x value, the y's are no longer unique. And that's why this one is not 1-to-1. I'm going to write that up here, not 1-to-1. So that's what you're looking for. The primary, not necessarily always, but probably the primary time that this is going to happen in this class is when you have a squared, is going to involve a not 1-to-1 function. And then at the end of the class, we'll talk about circles. When you go beyond this class, if you take pre-calculus, there's lots of other functions you're going to encounter that are not 1-to-1. So you'll expand your list of functions. So you might be thinking, oh, this is all great, Perkster, I love this, but why do I care if something's 1-to-1? Why do we have this new detail? And that is a great question. I'm glad you asked it. And so the answer to that question is, if a function is 1-to-1, then it has this important property for us. Then its inverse is a function. Then that raises a whole new question. What in the world is an inverse? And that's a great question. I'm going to define that, but I'm just giving you a moment to write that down. So the reason we care about 1-to-1 functions is when a function's 1-to-1, its inverse is a function. And now if you're thinking, what in the world is an inverse? I didn't leave myself, not good planning at all, didn't leave myself enough room. So I'm going to write below this example, we're going to do what the inverse is. An inverse is just what you get when you switch the x and y values. Okay, so the inverse is just what you get when you flip the x and y values. Okay, So I'm going to go back to page 1. Okay, so on page 1 here, example 1, we determined that was 1-to-1. And so by what I just told you, that means the inverse of that is also going to be a function. So what is that inverse? So we're going to do that right now. The notation for the inverse is I'm going to use the same function letter, in this case an F, and then you put a little -1. If that's not an exponent, it's a superscript. So it's, but it means the inverse. So when I do the inverse of this, I'm just going to go through each of my ordered pairs, and I'm going to swap the x and the y value. So instead of -5, 1, the first point is 1, -5. Instead of 3, 5, the next one is 5, 3. Instead of 6, 9, it's 9, 6. And then last but not least, instead of 8, -6, it's -6, 8. And there is my inverse function. And you can notice, since none of the x's are repeated, it is a function. That was our definition way back in chapter 2 of what a function is. So in the 2 exercises you did to follow up example 1, I'm interested in the inverse of one of them, the one that's 1-to-1. So if you would find the inverse of the 1-to-1 function of those exercises. All right, so hopefully what you wrote down is this. For exercise 2, I'm not interested in the inverse of exercise 1 because the inverse is not a function. I am interested in the inverse of exercise 2. So that inverse, the f with the little -1 as the superscript, looks like this. It is 2, 2, and then 4, 3, and then 6, 4, 8, 5, and 10, 6. There's my inverse. All right, if I turn to page 3, top of page 3 is going to give me this instruction right here. It says, my next example that I'm going to do along with you says, graph the inverse of example 2 on the same Cartesian plane. Okay, so we're going to go back to page 1, and I'm going to graph the inverse of example 2. So let me find a nice, distinct new color. We'll use this lovely pink right here. And so what I'm going to do is I'm going to graph the inverse. All we're going to do, since the inverse is what I get when I flip-flop the x and the y, I'm going to go to each of the ordered pairs and flip-flop the x and y. So this first ordered pair, what is this ordered pair right here up at the top? It's 2, 10. Great. So the inverse is going to be 10, 2. The next one is 1, 3. So the inverse is going to be perfect, 3, 1. Well said. The next point here in the middle is 0, 2. So when I flip those around, I get 2, 0. -1, 1 is the next point. So when I flip that around, it becomes 1, -1. And then finally, this last point down here is -2 and -6. So it becomes -6 and -2. And so now I'm going to connect the dots. And you can see this is the graph of the inverse. And the reason that I had you do that on the same Cartesian plane is I just wanted you to see the pictorial relationship. They look very similar. They actually look like reflections of each other, I think. And that is true. And in fact, there's a particular line that these two things are reflection about. And this is a property of inverses. So if I draw this line y equals x, the line where the y value and the x value are the same. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 0, 0, -1, -1, -2, -2. I'm just going to make a dotted line here. If I draw this line, y equals x, a graph, a function, and its inverse are symmetric about the line y equals x. It's the same thing on both sides. If I was to fold that Cartesian plane along the line y equals x, those two graphs should match up perfectly. So this is my line of symmetry between a graph of a function and its inverse. So exercise 3 was not one-to-one. We're not really going to have time to address it in this class. But again, if you take pre-calculus, you'll get into this in a little more detail. What I would do is if I wanted to work with this, I'm not going to ask you this on the test. I'm just giving you this for fun knowledge. What you would do is called limit the domain. Whoops, A-I-N. You'd limit the domain and you'd only consider one half of the graph or the other in order to make it one-to-one. So for instance, I'd limit the domain to 0 to infinity. So I'd only consider the right half of the graph, and then I'd have a one-to-one function. And then I could find the inverse and I could do stuff with it. But that's going to be a little beyond what we have time for, because inverses are already difficult enough. I don't want to have to just rush through stuff. So what I would like you to do is in exercise 4, which we saw was one-to-one, I want you to graph the inverse of that for me. Take a moment or two and do that. And then once you've done that, I would like, because I want to show you another little thing, I would like you to find the domain and the range of both the function and its inverse. All right, so I'm going to flip-flop these points. So starting over here, I've got the point 6, 3. Let's not use the same color. That would be totally confusing. 6, 3, so I'm going to reverse that to 3, 6. So 3 and then up 6. This point is 1, 2, so I'll reverse that to 2, 1. This next one is -2, 1, so it becomes 1, -2. And last but not least, -3, 0 becomes 0, -3. And so here is my inverse. Again, you can see the symmetry about the line y equals x. I also asked you to do the domain and the range of the original function and its inverse. So help me out. For my blue, the original function, the domain, where does that start? What's the furthest left that is? -3, indeed. And then what's the furthest right that one goes? Positive infinity. And then the range of the blue one, what's the furthest down that goes? That's right, the lowest y value is 0, fantastic. And what's the largest y value going to be? Infinity, yeah, it's very slowly doing it, but it's gonna just keep going up, 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 up forever. Okay, so there's my domain and my range. Whoops, that should be a parenthesis. Now here's the thing. To find the inverse, we just flip-flopped the x's and the y's. So here's my expectation, is that since I flip-flop the x's and the y's, I'm thinking that the domain of the function then becomes the y values or the range of the inverse. Okay, so let's see if that's true. Okay, so that gives us another relationship between these two things. So looking at the red function, the domain of the red function. So what's the furthest to the left the red function goes? X is 0 right there in the middle. And then what's the furthest to the right? How far right's this one going to go? Infinity. Yeah, it's going, again, it's going slow. This one's going up more than it's going right, but it's going to get there eventually. And so 0 to infinity. And then the range, what's the lowest the red function goes? -3. Yep. And then it goes up to infinity. So notice my expectation was met. Okay, the domain of the original function becomes the range of the inverse, because the inverse is just what we get when we flip-flop the x's and the y's. Questions so far? Because we just got one more thing to do, and we're just going to do the one section today because it's the day before spring break. I couldn't push this to after spring break. Sorry, just because then we'd feel really, really cramped for time afterward. All right, so here we go. Last thing, my last example for the day, example 6, says, okay, we've learned what a one-to-one function is. We've learned that that's significant because one-to-one functions have inverses that are function. And so we found inverses by manipulating graphs and manipulating sets of ordered pairs. The last thing we're going to do is we're going to find the inverse analytically. So example 6 is I've got f of x is equal to x cubed plus 2. And I want to find the inverse. Okay, so here I'm going to rewrite my function f of x is equal to x cubed plus 2. And I'm going to help you with the steps. Step number 1. Step number 1 is purely notational. All you're going to do is, instead of having the f of x notation, you know, because I've asked you this like a dozen times over this semester, that f of x means y. So I'm just going to change that to y equals x cubed plus 2. Okay, that's step number 1. Step number 2. Step number 2, this is going to be the inverse step. We are going to swap the x and y. Okay, and I'm going to put in parentheses, this is the inverse. I'll put an exclamation point because we're super happy about it. Okay, so we're swapping the x and the y. This is the inverse. Oh, I didn't write down that though. So x is equal to y cubed plus 2. So notice I left the cube where it was. I didn't put the x cubed on the left. I just flipped the place of the x and the y. That's the inverse. And then the last thing you're going to do, or actually second to last thing you're going to do, is you're going to solve this for y. We traditionally write our functions solved for y, so we are going to continue to do that. All right, well, it's 2 steps for me. Step number 1 is I'm going to subtract 2 from both sides. Okay, so I'm going to have x minus 2 is equal to y cubed. And then step number 2 is I'm going to take the cube root of both sides to get that y by itself. So let me grab a different color just so that this is distinctive. I'm going to take the cube root of both sides. And what I end up with is y is equal to the cube root of x minus 2. So just like the first step of this was purely notational, the last step is purely notational. Instead of leaving this y equals, I'm going to rewrite this in function notation, and I'm going to write f with the little -1 of x. Okay, that's inverse function notation, is equal to the cube root of x minus 2. So again, just running through the steps real quick. We started off with this function. We have shown twice. We've shown by graph. We've shown analytically that this is 1-to-1. So we know that the inverse of this function is also a function. So here's the process for finding it. The first step's notational. You change the f of x to a y. Then the second step is you actually find the inverse. And the inverse is what you get when you swap the position of the x and the y. So we swap the position of the x and the y in step 2. And now that my y is in this position, the y is cubed. So the big step, step 3, is to solve for that. And we did that. We subtracted 2, took the cube root. And then the last step is notational. And we put in the inverse function notation. So what you're going to do, we're going to do this just 3 times because this is the kind of the meat of this section. I would like you to do exercise 9. I want you to find the inverse of f of x is 5x minus 2. And let's see how you did on this first one. So I'm going to rewrite my function. F of x is equal to 5x minus 2. Step 1, I'm going to take that f of x and I'm going to make a notation change. I'm going to make it a y. So y equals 5x minus 2. Then this is the big step right here. This is it. I'm going to flip-flop the x and the y. This is the inverse. So I'm going to have the x over here and then 5y minus 2. Again, notice everything else stays exactly where it was. It's only the x and the y that I change positions of. And then I solve for y. So I'm going to add the 2 to both sides, and I get x plus 2 is equal to 5y. Then I'm going to divide both sides by 5, and I get y is equal to x plus 2 over 5. My final step is, again, notational. Instead of y equals, I'm just going to write that f with the little -1 superscript of x is equal to x plus 2 over 5. All right, one more time, exercise 10. And if you got a question, wave your hand. I'll come help you. Happy to be of service if I can be. All right, so once again, I'm going to rewrite my function. F of x is equal to x minus 4 cubed. First step, purely notational. Change that to y equals x minus 4 cubed. Got that? The inverse, flip-flop the x and the y. So I'm going to put the x over here, and then y minus 4 cubed goes over on the other side. So I changed their position. That is the inverse. And now we're ready to be done. I'm going to take the cube root of both sides. So I have the cube root of x is equal to the cube root of y minus 4 cubed, which just leaves me with y minus 4. And then I'm going to add the 4. So I've got the cube root of x, and then outside of it, I've got plus 4. Last step, I'm going to, instead of have y, I'm going to put it in function notation. There's my inverse function notation. And then I have the cube root of x, and then outside of the radical plus 4. And there's my inverse. All right, the last thing for us today is the last exercise. Exercise 11 gives us two functions and says, okay, demonstrate that these two things are inverses. Now, one way you could approach this problem is you could start with the function f and find its inverse and come up with the other one and say, yes, they are inverses. But I'm going to show you another tactic because, again, when you get to pre-calculus, okay, it might not always be easy to solve something for y, or you might have some trigonometric functions, things. So there's another way to show things are inverses that works when you have slightly more complicated functions. Okay, so for a simple situation like this, you could definitely find the inverse and it's going to end up like that, and you've definitely shown. But the other way to do it is this. If I used my skill of function composition, I can show if two functions are inverses, and here's how. First, what I'm going to do is I can take f of g of x, if that equals x, and when I flip it around, g of f of x, if that equals x, then you have two functions that are inverses. So what this is saying is if I take an x value and I impose the function g on it, okay, so I go in one direction, and then I turn around and use the function f, I should end up where I started. Okay, that's what this function composition is saying. That whatever order I do these two functions, I should end up with exactly the value that I started with if they're both inverses. So just because I know function composition was a while ago, I'm going to do the first one, and then I'm going to give you a minute or two to do the second. So f of g of x, and I want to know, does this equal x? Will I end up where I'm started? Okay, so here goes. So f of g of x is going to be, I take the function f, and I'm going to plug g of x in. So I'm going to plug x minus 2 over 3 into that function. You with me so far? I know function composition was a while ago, and we jetted through that section because there was function addition and subtraction and all that good stuff was part of that section. So I just took this function g of x right here, and I put it in the parentheses, x minus 2 over 3. And now what that says I'm going to do is I'm going to, in the function f, wherever I see a variable, I'm going to plug in this mess right here. So my function f is 3x minus 2. So I'm going to write that as 3x, I'm going to put a space, minus 2. And inside that space, I'm going to put in whatever the function g of x was, x minus 2 over 3. And now I'm going to simplify that. I'm going to see what I get. If I get anything other than x, okay, if I get x plus 1, anything else, it's not an inverse. Has to come up to be x. So here we go. So first thing I see is these 3's will cancel. That's great news. So I have x minus 2. Oops, I made a mistake. The function f is 3x plus 2, and I put a minus. So that should be a plus 2. Sorry about that. And then the negative 2 plus 2, since I fixed my mistake, the negative 2 plus 2, those cancel, and I just have x. So at least going in that direction, we have inverses. By the way, again, when you get to pre-calculus, you can have functions that are called left-handed inverses or right-handed inverse, where they work one way but not the other way. Okay, so there's lots of fun details that we don't get to talk about, but it could be part of your math future someday if you go for far enough. So if you would, last thing for us today, if you could now do the function composition in the other direction, if you could take g and compose it with f of x. And that will take us to our finish line today. So my g of f of x, I'm going to take the function g, And inside of it, I'm going to put f of x. And I see from the beginning, f of x is 3x plus 2. So instead of having an f of x in the parentheses, I'm going to put the 3x plus 2 in the parentheses. My function g is whatever the x is minus 2, all that divided by 3. So whatever the x is minus 2, all of that divided by 3. So I just leave a space where the x is. And now I'm going to fill in that gap here with the 3x plus 2. And now we'll simplify this. Up in the top, I've got 3x plus 2 and minus 2. So the 2's cancel, and I'm left with 3x over 3. And then that's lovely. The 3's cancel, and I'm left with x. So because the function composition produced x both ways, that means these two functions are doing the exact reverse of each other. You end up just where you started, and that means that they are both inverses.